Hey folks, this is Major Jones here to talk to you about our second Vhdl lesson. In this lesson, we are going to expose you to a couple more constructs so that by the end you can build in Vhdl any of the sequential logic devices we've seen thus far in our class, which include our SR latches, our D latches and flip-flops, and our counters. So we are going to by way of example, we're gonna build a mod 16 counter today in Vhdl. Okay, so here's a little block diagram of that device, and so it's gonna be a very simple device. I want an asynchronous reset. So whenever this will be active high reset. So whenever I toggle this reset line high, my counter should go to 0, and then on every clock tick, on every positive edge, the output will increment. Right, it'll go from 0 to 15, then back to 0 again. So to do this in Vhdl, we have to teach you a couple of things. We're going to go over 5 concepts today in Vhdl that will allow us to build this device. Okay, the first one is, we'll look at our sample code right here, right? So I've got this color coded, and so the first one we're going to look at is this stuff in purple. Well, maybe I should start with first kind of orient yourself. Right, we got our magic words up top. I'm defining our port. Our device here in lines 5 through 9, and I've got the architecture down below. And so what I'm saying is that there are 2 1-bit signals going in, clock and reset. I have my Q value coming out, the counter value, and then for demonstration purposes, I'm going to add another output to this block that's big num. So it'll be a little signal when our counter value is larger than some value that we'll get to in a second. Okay, so the first problem I'm going to try to tackle is colored here in purple, which is this idea that my output Q has 4 bits to it. So far, we've only kind of introduced to you the STD logic kind of data type that lets you store a single bit, 0 or 1. But of course, in an example like this, and in many others I'm sure you can think of, it would be exceedingly useful to be able to represent signals that have multiple bits to them. And the way we do that in Vhdl is to use the data type called STD logic vector. So not STD logic, but STD logic vector. It's a vector. It's an array of bits. And so this tells Vhdl, hey, we've got sort of a chunk of bits here. We're dealing with a 2 or a 4 or a 16-bit sort of number or signal. And to tell Vhdl how large that signal is, I specify these values. Right? 3 down to 0 means I've got an array Q here of bits that go from 3, 2, 1 to 0, so it creates a 4-bit signal that can go from 0, 0, 0, 0 all the way up to 1, 1, 1, 1. So that's useful, right? I can refer to Q in that form now as a single number with 4 bits to it, and you'll notice down here in this other purple box, if I'm going to sort of assign that signal values, this is a different signal, but it's the same range. Then I'm using double quotes around my value. So whereas R here was STD logic, we use single quotes around the 0 or the 1 to assign to a STD logic signal. If I have a vector, STD logic vector, I use the double quotes around those numbers, right? So this lets me create a 4-bit output, Q. That's number 1. All right, number 2 is I'm going to go back to my counter, right? I need to effectively on this device when the clock goes high or on the positive edge, then my counter value just needs to increment by 1. I need to be able to add a literal 1 to the value. And one problem with STD logic vectors is that Vhdl has no concept of this data type having anything to do with arithmetic. It's literally an array of, just one, an array of bit signals. So in order to do math, like down here you can see what I'm trying to add 1 to a number. I need to, number 1, I need to include a slightly different library. So I'm going to include IEEE.numeric_std_all. And furthermore, I'm going to make an internal signal which is not a vector, but unsigned. Okay. So what I'm telling Vhdl is that this signal Q internal is representing a positive integer. Right. The fact that is 3 down to 0 means there's 4 bits to that signal, so that number can represent literally 0 to 15. And I kind of need this. in other formulations, other future career paths, it's possible to make Q itself an unsigned value. The problem that we have right now with our software is that when we go to simulate this thing in the waveforms are going to expect the outputs to be, even if we label it as unsigned, it's going to try to treat it like a STD logic vector, and then we'll have sort of a data mismatch. Okay, so we have to jump through a little hoop to be able to make this work with our simulation, and that little hoop is to make a sort of an internal signal, which is unsigned. And you can see down here, I'm converting my internal signal into a STD logic vector and assigning that to my actual output Q. All right. So on my and my counter here, once this is actually simulated, this output here is a STD logic vector, right? That's Q, my signal Q. But inside my mod 16 counter, I'm telling Vhdl, okay, we're going to create this little internal variable, Q internal, which is an unsigned number that lets us do math, right? And there's a couple of things you can do with unsigned numbers once you've got them. So you can do not just addition, but subtraction, multiplication, division. You can shift. You can still do your bitwise functions, so your ANDing and your ORing. So lots that you can do with this library when I have an unsigned number. Right? Okay, so that allows me to do my addition. Lastly, let's kind of get into the meat now of this architecture and look at this little blue box here, this rising edge clock. Okay, so what I'm doing here, the heart of this counter is in lines 14 to 16, and what I'm doing is I'm saying Q internal. I'm using the when else construct, right, to sort of describe the behavior between the reset line and the clock. So what this is saying is that my internal counter value, whenever R equals 1, so whenever that reset value, that reset line is high, then Q internal just automatically gets 0. So it's reset to 0. And as long as R is not 1, so else, Q internal will get itself plus 1 when rising edge clock. And so this is a sort of VHDL keyword that says when our clock input here, when it has a rising edge, then sort of for that moment briefly, this little blue box sort of evaluates to true. So it's on that rising edge, as long as the reset line is not high, that Q internal gets incremented by 1. And effectively what this does is part of what creates sort of the flip-flop, creates the internal memory that allows the counter to sort of trigger and store values. So part of it is, this little kind of part here, the fact that I'm sort of triggered by a positive edge on a clock is kind of captured in this phrase right here. On the rising edge, Q internal gets Q internal plus 1. And then the fact that this thing has memory is actually implied by the fact that my conditionals here don't cover all of my cases, right? There's a time potentially immediately after the rising edge of the clock, if the reset line is not true, when neither one of these conditions are true. R is not 1. The clock does not have a rising edge, because it's just passed. And in that case, because I haven't specified what should happen to Q internal, in VHDL, I'm implying that its value should not change. I'm implying that it should be remembered in some sort of latch or flip-flop. All right. So the blue blocks here, in conjunction with the fact that I'm not specifying all of the possible conditions for my signal Q internal, are what together create this the flip-flop, the counter. Okay, so we are almost ready to finish this design. Actually, we're finished really with the counter portion, but like I mentioned previously, I'm to kind of expand on this a little bit to just show you that VHDL, I can define any number of outputs I want. What I have down here on line 20 is one last sort of combinational output, big num, which is going to be true when my counter value is greater than 7. So notice here, I'm using Q internal because I want to be able to sort of use the unsigned comparison, right? These little relational operators, and so I can do that even with, in this case, the unsigned. Actually, I can also use a number without quotes to assign to that internal value. So I can do this comparison when a counter value is greater than 7. Then big num equals 1, equals 1, and this is just to kind of show that I can add as many outputs as I want to my VHDL modules, and I can also do comparison with my unsigned numbers. Okay, so if I go to Quartus, all right, I just compiled this. This is a slightly different version we'll look at next, but functionally it's the same. And what I'm going to do is, let's go here to files. Let's open up a waveform. And I don't want to change some settings real quick. Perfect. Let's change my clock. Let's get a little bit on that. Okay, that looks good. Check my settings. Okay, run function. All right, so this is us simulating that counter, just to show that it, in fact, works. Okay, I'm resetting here, so my output is initially 0, and each clock edge I increment 0 to 1, 2, 3, 4, 5, 6, 7, 8 on the next clock cycle. Now my output big num is true because 8 is greater than 7, 8, 9, 10, 11, 12, 13, 14, 15, and then back to 0. So yeah, there's my counter. Okay, so that works. All it required us to do is to use the STID logic vector to create a little 4-bit signal, right, for my counter value. It required for me to use the numeric standard library and create this little internal signal that was of the type unsigned so that I could do math. And the last thing I needed to do was to include this rising edge clock to sort of configure this as an edge trigger device, as basically a flip-flop, right? Okay, the last thing I want to point out about this code right here is I've got this little comment on line 15 that says this value rolls over automatically. So I just want to elaborate on that really quick. You'll notice in the waveform, right, that once I got to 15, I went back to 0. That happened. It was almost a coincidence. So I want to make sure this is very clear, right? I've got a 4-bit vector here, and so it can hold a maximum of 4 values, which means when I add 1 to Q internal when it has the value 15, it's it just rolls back over to 0. If there were more bits to the signal, it wouldn't necessarily go to 0. It would go to 16 or 17, right? And so that's important because if I want Q internal, like if I want this counter to roll over at 12 or 13, it's not necessarily going to do so automatically. I might need to add some code here that says, okay, Q internal, it gets itself +1 unless it's 12 and then it goes back to 0 or something, right? Some of the logic may be a little more complicated if I'm trying to create like a different mod counter, right? Okay, so then let's take a look at one variation that introduces our last 2 concepts that will definitely be important a little later in the course. All right. So this is code that does the exact same thing. It just does it slightly differently. It uses here in red here. You can see these little keywords called process. All right. So what we can do is we can begin and end a process that sort of separates this little chunk of code inside our architecture. And inside a process, VHDL lets us use constructs that wouldn't make sense otherwise. So in particular, the if-else if. So in VHDL, I can write out sort of like a conditional chain that evaluates at Q internal to different values based on whether or not some conditions are met. But I can only do that inside a process block, right? And so we'll get to the if statement in a sec. What I want to say lastly about the process block is that what comes after the actual keyword process in here in parentheses is something called the sensitivity list. All right, and the idea of the sensitivity list is that what we're telling VHDL effectively is every time a signal in the sensitivity list changes, then generate hardware such that the stuff inside the process gets reevaluated. Okay, so what we're saying here is anytime the reset value or the clock value changes, then make sure that Q internal gets a new value based on those things. All right, so effectively, if I've got any signal inside my conditional statements right here, I've got if r equals 1, else if rising edge clock, right? So then clock and r, by virtue of being sort of inside those Boolean expressions that I'm testing, those two signals should be in my sensitivity list. Is kind of the takeaway, right? And then other than the syntax, which is a little unique of the if chain, right? I've got if something, then something happens. Else if, ELSIF, rising edge clock, then something happens, end if. The syntax itself is a little specific to VHDL, right? But the idea of a conditional chain, hopefully, is not new to you. And the only keyword I'm not really showing here is there's an else keyword, right? So, of course, which catches anything at the end of the statement, that the conditional chain. And let's see if I can zoom out real quick. Hopefully you can see at this point that this code right here, lines 14, 15, 16 on the left-hand side that assign Q internal using the when else are functionally the same as the if statement on the right, lines 16 through 20. In both cases, we're saying priority goes to the reset line, regardless of what's happening on the clock. If the reset line is 1, then Q internal goes back to 0. And if that's not true, then on the rising edge of the clock, Q internal gets incremented by 1. And even though the code on the left is a little more compacted, you could probably imagine the code on the right allows for much more complex kind of change. And in fact, one thing that I maybe should mention is that the if statements can be nested the same way they can be in other programming languages. So the if statement is has much greater sort of flexibility in letting us create complex designs. And in order for that to work, at least in VHDL, it has to be inside a process block. So those are the last two things we want to talk about today. You've got everything you need to on the left-hand side to build this counter, but we're going to start using, you'll see as we get into more advanced applications of VHDL, we start using the process block because we kind of need that in order to be able to describe the complex designs that we're going to in the future. And lastly, some folks maybe have seen this already, but I want to make sure you know that if you go to Tools, once I've compiled it, I can go to Tools, Netlist Viewers, RTL Viewer, and Quartus will show me the sort of block diagram for my circuit here, and I did this both ways. Both of these two chunks of code produce the same diagram, which you can use to kind of confirm that the code is functionally equivalent, and also just as a sanity check to make sure this is doing kind of what we want it to, right? So what this is showing me is that I've got a 4-bit sort of little D flip-flop, right, or a set of 4 D flip-flops triggered by my clock, and that which have an asynchronous reset, right? A reset line that can force this thing low regardless of what's happening on the clock. And the output here goes straight to my output Q. It also wraps back around to this little adder, which is adding the value 1 to that. And so on the clock edge, then this thing gets, one added to it. And I've also got the output here, which is being compared to hexadecimal 7. And if that's if it's greater than 7, then my output Vignum becomes true. Right? Okay, so those are the 5 things we want to talk about today. We wanted to introduce in purple the STID logic vector, in orange the numeric STID library and the unsigned data type, which lets us do math, addition, subtraction, and also the rising edge keyword, which helps create the flip-flop for this counter. In conjunction with the fact that there's sort of an implied it's implied that Q internal will hold its value when these conditions aren't true, which sort of creates that little memory. We also introduced the idea of the process block in red here, which lets us use, lastly, in green, the if statement, which we'll use much more on later on in the course. And in either case, both of these chunks of code produce our mod 16 counter. All right. So that's all I got. Thanks for listening. I'll see you next time.